Today I am going to continue my study of Boolean algebras, and I'm trying to understand them. Like, it's not that whoops. Like, I'm really not here to teach anyone about Boolean algebras. I'm really here to just understand them myself. 1 second. So, we'll see how I do this. I might use Canva again. That's cool presentation software. All right. All right. All right. I'm exploring. All right. 1 second. Before I get into this thing that happens a lot in my thinking in mathematics is like, um, darn, I might be a little too tired to do this. One thing that I've been thinking about is this. Let's say that someone says, or let's say I say, I want to understand Boolean algebras. Like, I want to understand, this and that property of Boolean algebras, this theorem, connecting it to this and that thing. And then I'm like, okay, let's do this. And then I'm like, wait, I don't even really know what the definition of a Boolean algebra is mathematically. So, at that point, I feel like it makes a lot more sense to discover the definition or the axioms rather than just looking them up. So then the question is what would motivate me to discover something called a Boolean algebra? And this is this thing that I've been thinking about a lot, but I'm going to look it up right now. I haven't had the time to go through this and see if it's really what I'm talking about, but the way that I see it, 1 second. Okay, now the way I see it, instead of looking up the definition, what if we try to discover it by motivating the discovery of it? And I think that, if you kind of formalize a lot of mathematical ideas in just formal logic, I recently came to think that a lot of answerable questions, like if someone challenges you to answer a question, prove something, I think right now it's basically just of the form. Okay, so first of all, luckily for us, everything in a logical system or a deductive system or whatever, we can say it's only of one category, which is formula, I think. So, and the next thing that I need to learn more about is sequent calculus and deductive rules and stuff. But let's just say that there's really just there is one most important concept or relation in deductive systems. This is this approach to logic that I've been thinking about, which is implication or entailment or deduction or whatever you want to say it. So let's say like the main character, how did this become bold, of logical systems, deductive systems, etc. is the deduction relation, implication, entailment, consequence, derivability, whatever. All right, just put in some arrows to make this look cool. Okay. Let's say that paradigm. Let's just say it's a paradigm. It's not a claim. It's more like an exploration of just holding this assumption. So this has led me to think that there's very often this could be completely wrong, but I've often been thinking that there's almost like two common recurrent questions that we encounter in math. One is like, one second. I give you a definition, darn definition, and you prove a property of that thing. I give you a definition for something, and you prove a property of that thing. The other is I give you a property and I ask you to find a definition for something which fulfills that property. Now, I think that this is a confusing and false way of splitting it up. It's kind of an illusion because one second. Because actually, wait 1 second. Now I will put a big red X over this. one's good. And I'm going to say, no, I don't like that. Because what is a definition anyway? This depends on some stuff that I need to study further. But as I've been learning a little bit of logic and model theory, which I need to learn much more about, is that you actually, everything is, as I said, a formula, a proposition, and I'm also considering that atomic formula are built solely out of predicates. And predicates are like it's like it kind of depends on the context you look at them in, because from one way of looking at it, it's the exact same thing as a property. So here's what I mean. I claim 1. Everything in a logical system is a formula sentence proposition. Some of this is not perfect. I can imagine people objecting to how I'm phrasing this. Oh well, I'll fix it later. 2, because it's not very clear when I say everything. I mean, like, what I mean is that, whatever. Yeah, I'm so sleep deprived right now. I think it's like my mind is not going that well. Everything in a logical system is formed, blah, blah, blah. All atomic formula are atomic formula. Sorry, no. Actually, they are either atomic formula or logical connectives, logical, constructions, let's say. I kind of want to say combinations, but now that has like a kind of specific meaning in math, I'll just say combinations or logical combinations of the atomic formula. Atomic formula can be seen as predicates. I'm being so imprecise here. I mean, like, that you can look at all atomic formula, in my opinion, as the application of of any of the relation symbols or the relations to any of the terms. And like the way that I learned it, there's a distinction between the relation symbols and the equality symbol, and I'm just really interested in the idea that like equality is just a relation. I mean, I'm sure there's different ways of looking at that, like why sometimes you really would want to keep them separate. but I'm actually exploring what happens when you just merge them together. And I'm going to say that for predicates or relations are the same as properties. And I'm going to show something that I've been thinking about lately. 1 second. Table, text, elements. Yes. No. Okay, I guess some of these are pretty useful anyway. What I've been thinking about is, let's try this one. No. Okay, there we go. Cool. Perfect. I think in here we have formal logic. Here we have natural language or grammar. And here we have what I'm calling like metaphysics. And it seems like there's a cool kind of it's like it feels like they're the same thing, but if you try to find the different corresponding words, it's like you can kind of realize certain things. So let's say in logic, like you start with some constants, and I think those are some nouns, and those are some things. Then you can have like variables. Those are roughly pronouns. And these are sort of like, I'm just going to make up my own terminology. I'm going to call them pointers, because it means that like in some situation where we just say that things exist, I think that pronouns imply that it's almost like there's a perspective. There's like some point of observation where amongst all these things, you're able to differentiate them and talk about them. So it's like, even when we try to think about the thing itself rather than like the language describing the thing, it's like once we get to I think once we get to variables, it becomes clear that in this kind of domain or something, that there has to be like the structural ability to direct attention and observe and describe. So it's almost like language is still a part of this like metaphysical way of looking at this. And I'm just going to keep saying this. I guess I'm really sleep deprived and I'm just not feeling at my sharpest right now. So I might just sometimes sound kind of banal, unfortunately. Oh well. Then we have functions. I'm not even going to worry too much about what that is. But the weird thing is that we use the word relation in logic to mean something that kind of gives it a truth value. But I almost think in natural language we could actually think of this as a relation, because I can say like my brother, and yeah. One second. How do I expand the table? I'm going to call this internal structure. Then we have terms. And we can say it's like more like a noun phrase, let's say. In this case, it just comes straight back to things, which is kind of cool. Okay, then we would have equality. I don't know if this is wrong, but I'm going to say this is like a copula, because that's like a special kind of verb in natural language. But it's already very stimulating because in natural language it's interesting how like we differentiate between like stating the equality of two things versus stating that something has a certain property, like, you know, the book is red or something. I want to think way more about this. And then, okay, metaphysics. This is something deep that I haven't really thought about yet. Let's go. I think this relates to like definite descriptions and stuff. I think the weird thing is that in the metaphysical scenario, when we say two things are equal, like equality is much less like powerful or meaningful when we think about this as like a collection of actual things. Because fundamentally, when we say that two things are equal, we're actually saying that two different pointers are pointing at the same thing. We would never really say that two things are the same thing. There's really just one thing, and if there's two things, they're not the same thing. So it's kind of like in certain mathematical scenarios, like I think in like free algebras or something, it's like you never have like two different elements of the free algebra that are like equal and mutually substitutable. That's the point. That's why it's a free algebra. And it'd be cool if there's some mathematical term for this where it's like you have a collection of elements and you sort of somehow say that you're not allowed to impose an equivalence relation on this set of elements. You're not allowed to imply that any of these things could be equal to any of the other things. In fact, that's like a precondition of understanding this thing, is that nothing is equal to anything else. Everything has a distinct existence, kind of. So I'm just going to say Relations. Again, this opens up interesting thoughts because, like, what's interesting is that it seems like in logic, relations are like really simple. Like, you can have as many relation symbols as you want, but like conceptually, it's very simple. You just apply them to terms, and then you just decide if they're true or false. But then in natural language, like, it's hard to simply say like, oh, what's a relation? Oh, it's like a predicate or something. It's like, yeah, but there's so many different kinds of predicates. There's like, I think there's like predicative adjectives. There's verbs. There's like, yeah. One second. I'm just gonna say predicates for now, but I'll add in like verbs. I don't know what else to say. I'll just say descriptions. There's more to be thought about there. And then this I find pretty easy. Properties. And this also relates to stuff that I'm trying to think about, which is like, to what extent can anything be associated with a collection of properties? And that leads me to this weird thought that I think is actually defensible or worth exploring, which is like, when I was trying to build some formal models of the world earlier, I would sometimes be very confused about the difference between a class of things and a specific unique thing. So like, there's there's a class of things which qualifies books, because books have certain properties as long as you fulfill those properties. Let's say you're a book. But then I was thinking, like, let's say a person like me, for example. I don't really want to say that, oh, there's a class of properties defining a me, a Julius, and then, oh, anything which fulfills those properties is a Julius. Like, it felt like it didn't make any sense. But now I've been thinking about that lately, and I'm thinking, like, what if that is actually a really interesting paradigm to accept? It feels definitely very metaphysical. It reminds me of things like multiple universes, parallel universes, where it's like, yeah, actually, in a way, you could see me as a collection of propositions or facts about everything that's happened in my life. And in theory, like, there are a lot of ways in which we can replicate information, and according to like human common sense, it's like it feels like it violates the uniqueness of our identity, and that it's like one of those deeply embedded ideas in like everyday discourse and culture, that when you start to think about like that it might not be wrong, or sorry, it might be wrong, it's like it has the potential to undermine a lot of different ideas in philosophy and in the humanities. For example, like cloning is philosophically fascinating. Like, if someone like comes into being who has my DNA, I think that there's definitely one angle nowadays where people would kind of feel a sense of personal ownership over their DNA, because they're like, that's me, But it's like, it's just really interesting to consider that it's possible to have multiple instances. If you define yourself by your DNA, it's possible to have like multiple instances of you, and it just becomes clear that like there is actually no intrinsic logically necessary reason why like personal identity is related to like uniqueness. There's actually no reason why there can't be a second instance of a person with all of the same like properties that define me. I just don't feel like I'm explaining things very well today, but I can develop these thoughts later. So coming back to this, I'm going to say properties, and I am going to explore this idea that I think, I can't remember if Russell kind of, I'll look it up because I know Russell and Kripke both like did some work on this, but my idea right now is that I'm exploring this idea that we actually don't even need the concept of like, I don't know if they're called definite descriptions or if they're just like, let's say like proper nouns or something. We actually don't need that. Yeah, and I think it has a lot of interesting potential because like I feel like in type theory, you have a type and then you have a term of that type, but it's like the way that I've seen it, every term can also be its own type, I think, or I want to explore type theory like that. And that's the point, is that it allows us to get rid of this weird just like distinction that we would have to accommodate. So it's like, let's say the type of all people. Okay, there's like these terms or these like instances of that type. For each of those terms, like we can just make that a universal thing. Like, oh, the type of this person, and it's like we don't need to like rebuild our system. We can just say, okay, yeah, this is this type of person. Like, just get like, oh, my neighbor, Hernando, and there's just no reason why we can't have multiple terms of that type. There's no reason why we just can't have multiple Hernandos. So that's the idea. It's like just getting rid of this assumption that there's like some things in the universe that have to be unique for some reason. Okay. I don't know, maybe this is like fleshed out enough. Then we could say we finally get to sentences or propositions or formula, and that's sentences, assertions, propositions, and that's over here it's more like facts or the case. And then we have theories, collections of formulae. I'm just going to loosely call this a discourse. Loosely. And I'm going to call this a possible world. I'm pretty sure I might really be venturing out of my terrain or whatever, but I'm pretty sure like the collection of all collections, it might be the Lindenbaum-Tarski algebra. This is like, I don't know. I'm really getting kind of loose here, but I'm just going to go for this. I'm going to call this the Library of Babel, which is like every possible kind of linguistic utterance in a way. Wait, is that what it's called? Oh my god. Yeah, that's it. And I'm going to call this All Possible Worlds, which is the multiverse or something like that, or beyond. I'm really being loose here. Okay, I just wanted to throw that out there. So coming back to this. Here's my idea. In other words, there isn't actually a categorical difference between proving something from a definition versus finding a definition to fulfill a property. Oh no, it's not working, is it? Darn. Which was what kicked this all off, is this question of how do I define something which I don't know what it is? For me, that's just this fascinating question. It's like, it's just, this is like this simple, concrete example in case, like, sometimes I just think that, I don't know, my ideas are kind of like speculative, and sometimes I have difficulty helping other people understand more clearly the idea. I think. I'm not sure though. But here's like, this is the concrete scenario. Is like, I have been told that there's something called a Boolean algebra, but I don't want to look up the definition. I want to figure out the definition. But that's where this idea of the paradox of analysis comes in, I think. One second. Which is like, whoops, one second. Oh. I want to define something, but I don't know what it is that I want to define. I'm just going to put it simply. And I'm pretty sure that this is what this is saying, is that if you already know enough about the thing to actually logically point to it and specify it, then you already have a logical definition. And so, sure, you can use that definition to prove further things about it. Okay, but that's not the same as, like, finding a definition in the first place. I think that's kind of the rough idea. So here I say like so this is my new way of looking at it. So like actually what's going on is that we start with P. We have to start with like a formula. And because like the deduction or implication relation is I think we could say that because it's non-commutative, or in other words, like it's ordered, the order matters, like A implies B is not the same as B implies A. It's basically, in a very simple way of looking at it, is that we have two ways of forming like an algebraic equation, with an unknown in it, basically. Sorry, that just gave me a weird, cool idea. We can either put forward our formula and ask what implies this, for which there may be more than one answer, or we can put forward our formula and say what follows from this. And just a couple side notes here. 1 second. Other options. What implies what? This is an algebraic equation over the entire space of implication. I'll just say over the entire logical space. We also have the option of, 1 second. Man, I just had a thought that it just disappeared from my mind. What was it? Whatever, it'll come back to me. So the idea is like, oh yeah, there it is. So based on this simple idea, I want to throw in a couple other ideas. We can take this implication function, let's call it, and let both arguments be variables and try to study, like, I guess the behavior of it as a function, you could say. We can do what I've been calling coherentizing, which is where it's more like machine learning, sort of. It's like you are going to look for a definition that fulfills certain properties, but you're gonna decide like if the property is adequate or not. It's like a process of, I think it could be seen as like almost like an inductive process. It's or almost like bootstrapping, where it's like, I don't know what the premises are, I don't know what the conclusions are, but what I can do is I can start with a simple premise, then I can study what conclusions it has, and then I can update and say, is this adequate or not? It's not. Okay, now I'm going to explore adding another premise. Like now we have two premises. And you go back and forth like that until you kind of like hone in on the definition you're looking for. So I'm trying to eventually I'm trying to develop that idea mathematically. And then there's undecidability, which is like, it turns out that something is just like completely independent, I think like, the continuum hypothesis is independent of ZFC or something. So if I wrote the continuum hypothesis, I could say like, what implies this? And the answer would be like nothing. And then if I said, what does the continuous hypothesis imply? Well, that actually has a lot of meaning. And I guess the sort of converse of this is like, yeah, there's interesting thoughts to be had there. This is interesting. Yeah, I need to think about this more. It's like some of these might not make sense, but here we have like nothing implies P. So you cannot derive a proposition from some axioms. But if you had that proposition in your system, it would imply something. When I say imply something, I basically mean like, I'm pretty sure what I mean is that the theory is no longer logically equivalent. It's, God, what do they call that? It's not a trivial extension. It's like a non-trivial extension or something. Here we have nothing implies P. It can't be derived. Now this, I don't even know if this is possible. It cannot be derived, but if you add it as an axiom, it would not logically change the theory. That's like an interesting idea. Something implies P. It's derivable. So this is kind of interesting because like this is what I would expect. It's derivable. Oh, actually no. There's different ways to think of this. This could be thought of as like it's derivable, and in a sense, adding it wouldn't change. It would be a trivial extension or something, because yeah, it's logically equivalent. Or you could interpret this differently. Maybe I need to now distinguish between these certain interpretations, which is like it is derivable, but it's just like a tautology. So even if I gave you this really interesting theorem or something, it's not going to help you prove like anything new. And here we have it's derivable, and yeah, again, there's actually two interpretations. One is like conventionally it's useful, let's say, like if I prove a theorem and then you can use that theorem to prove new things, versus it's derivable, and the weirdest thing is like it updates the the character of the logical system. Like that would sound like a contradiction, but it would be cool if we could find a way to modify that idea, because I think this makes us think about the difference between like the collection of truths that a collection of formula determines, versus like those which we know of. Like, how are we going to figure out the ones that we don't know? Sort of, I don't know. There's a lot to be thought about here. this is like an opportunity to expand on these ideas later. Oops. This is like a whole bunch of questions that I've had for a while that I haven't had time to start exploring, but I should. All right, here, it seems we need to further distinguish between what is true versus what is known. Okay. Double indeterminacy or something. Okay. Now, where am I going with all this? Maybe that really sums up what I wanted to say, honestly. That's the idea, is like, if I want to figure out what a Boolean algebra is, I think that what I call coherentizing, maybe it has like a much simpler name. It's really just how people try to figure out the world through, hypotheses and stuff. So I think that that is the way in which I can actually try to discover a definition. And maybe I should say like the first part of the video ends here, and then like in the second part I'll actually try to do that. That would be fun. I also feel like there might be something I completely forgot to say, because I wanted to say something more about, I think, like where this was leading me. But maybe that was it. Yeah, maybe that was it. Okay, that's the end of part 1, and then I'm about to start part 2, which is like, okay, so let's try it. I'm gonna do this in a more subjective way, or instead of trying to write some kind of algorithm, which is something I want to do later. I'll just write that here. First, try it subjectively. Later, make it computationally enumerable? Question mark. Then that leads me to a question that I've had for a very long time, which I find extremely essential. Which is like, I believe that every formula in a deductive system, or the deductive closure of a collection of formula, which I'm going to call theory, can be assigned a degree. The degree is the number of applications of the rules of the deductive calculus you're using in the shortest proof of that formula. And luckily, there's this theorem, I think, that some logics are normalizable. And I think that means that they have a they have a shortest form, I'm actually looking for a cool way to define that, but for now I'm just going to speak very intuitively. Like, you can always like reduce the proof. You can like, it's like algebraic simplification or something. So in this case, I might try to get a little bit of help from, looking something up. But first, I'm just going to try to hypothesize how I see this happening. One thing I need to do is I need to make sure I understand sequent calculus, because I've been meaning to do that forever. Because I feel like I still don't really grasp it that well. First, grasp sequent calculus. Next, observe patterns in the smallest, I'm just going to call it a degree of a proof. The number of steps in the shortest proof. Let's just start here. Man, yeah, I'm very tired, but I'm going to push through. Okay. Oh yeah. Gotta get this in here. Put that over there. Now this is like some very good exercise for me. Because I just, this is like a very nuts and bolts thing that I have been meaning to work on. And I'm gonna try to explain my understanding of sequent calculus, and then I'm gonna check if it's right or wrong. Alright, let's say that first we have formula. Let's say we have 10 rules, and this might be wrong. I'm going to try to remember some of the rules. I'm trying to come up with some of the rules. Here we go. Or maybe I'll just look them up. 1 second. Yeah, I'm not gonna try to impress anyone here. I need to study this more. I'm just gonna study it now. I actually might not even need this. Maybe I should just start with like natural deduction. It seems a lot easier. Yeah, I might actually not be ready for sequent calculus. A rooted tree, describing a proof finding procedure by sequent calculus. So here we have nothing entails this, so it's sort of like an axiom. P implies R, or Q implies R. Oh no, actually, I might be wrong here. Maybe it goes upwards. Commutativity. Oh yeah, this one. This is called, I can't remember what this one is called, but I like this one. Okay, and this is, 1 second. PQ plus PR. Oh, that's not commutativity. Never mind. I don't know where this axiom comes from, honestly. Maybe it's, yeah. I guess it's an axiom, so I don't need to ask where it comes from. I don't know. Yeah, okay, I guess so. Put these together. Yeah, I think I need to do an entire presentation just on sequent calculus because I do not understand it well enough. Yep, I'm just gonna do that right now. Alright, farewell. I'll come back to this. I'm gonna study sequent calculus on my own. Thank you.